So, yeah. Hello everyone. I'm Kailash Prasad, PhD scholar from IIT Gandhinagar. We have this session every Tuesday on the course Digital Circuit taught by Professor Santanu Chattopadhyay. And the goal of this session is to discuss some of the concepts, some of the questions on the concepts which are discussed in the class. Uh, I hope you guys are following the NPTEL Digital Circuit course. So we'll be discussing some of the questions which are based on this week's assignment and the next week's assignments and the lectures. So as of now, what we have done is we have started with week one, where we have discussed about the number system, Boolean algebra, combinational function minimization. Along with that, we have discussed logic. We further discussed arithmetic circuits like code converters. After that, we discussed some of the combination circuits like multiplexer, decoder, PLA. We have also discussed a couple of questions on sequential circuit, latches, flip-flop, counters, shift register, and FSM. Last in the last lecture, I had a detailed session on milli and Moore FSM, where I have taught how to design milli and Moore FSM for both overlapping and non-overlapping sequences uh, for a sequence detector. Okay, and also in the last lecture, I have sold a couple of questions on data converters for ADC and DSC. Uh, so that was the last lecture, right? The sequential circuit and the after that we discuss counters. After that we discuss data converters. In this lecture, what we'll be discussing is what we call as semiconductor memories. Along with that, we have some of the questions on analog to digital converters. Okay, so we will start. If you guys face any problem, if you are not understanding anything and the questions which are solved, you may ask. Okay, so every time I say that ask a question, you should ask questions if you don't understand. So we will start the session. It's a first question, and it's a very simple one. I just will tell you how to approach this question. So the question here states that find the binary output voltage. Okay, so this binary input output we have to find Q2, Q1, and Q0. Okay, for the input voltage Vin equal to 4 volt. So where is the Vin is applied? So Vin is applied over here. You can see 4 volt. Okay, and Vref is 6 volt. Okay, it is 6 volt. So and what I want is what will be Q2, Q1, and Q0. Anybody wants to answer this question? Anybody? What will be Q2, Q1, and Q0? If this is Vref is 6 volt and Vin is 4 volt, what will be Q2, Q1, and Q0? Anybody? You have done this kind of questions, right? Option A. Okay. Khalid is saying option A. Any other answer? Okay, so what we will do is it's see approaching this kind of question is very simple. What you have to do is you have to find out what is the voltage at each of the nodes. Okay, each of these nodes. So this node, right? And then what we will do, we will compare all of this voltage with 4 volt. Please note that this is a comparator. This comparator will give output. Okay, 0. Okay, uh, so this will give output 0. If my V in input signal, so the negative terminal signal is greater than the positive terminal signal, okay, and it will give 1. So see, the output will be 0 for this comparator if your V is V means V negative, right? So V negative is greater than V positive, and 1 if V positive is greater than V negative, right? So this is the concept we'll be using over here. I hope everybody understand this. So this is the basic concept of the comparator, and what we'll be doing is we will quickly calculate whatever the voltage we are getting over here. Please note that this is 6 volt, okay, and we have 8 resistance in series. Okay, R1, R2, 1, 2, 3, 4, 5, 6, 7, 8, And please note that in the op amp, right, in the comparator, there won't any be current which will be flowing inside, right? So whatever current that will flow by this path. So this is a resistor divider network. Okay, so whatever voltage you will get over here will be divided into 8 parts. Okay, so how you have to approach this problem? So if this is your vref, which is 6 volt, right, you can write this as so you can multiply this as like this. Okay, 6 multiplied by 8 by 8. Okay, so this point you can write like this. This node is connected by 7 register, so you can write 6 into 7 by 8, right? So that will be 42 by 8, right? Similarly, this will be 36 by 8. Okay, so this will be 30 by 8. So this will be 24 by 8. Okay, this will be 18 by 8. This will be 12 by 8, and this will be 6 by 8. Okay, so this is how the voltage will be. So what we have to do now is we have to compare this voltage with the other voltages. Okay, so the positive and the negative one. So what we will do, we will just compare. So see, the 42 by 8 means 8 5s are 40, so greater than 4 volt. So whatever voltage you will get over here will be greater than 4 volts, so this will give 0. 36 by 8 means 8 fours are 32, again greater than 4 volts, right? So this is 0. 30 by 8 means 8 fours are 32, right? So this voltage will be lesser than 4 volt, so you will get 1, and all the remaining voltage will be lesser than 4 volt. Okay, 1 1 1 1, like this, right? So the input to this 3-bit priority encoder is 00111111, right? Please note that this is priority encoder, right? So if the multiple input of a priority encoder goes high, the priority will be assigned for the most significant bit, right? So the priority will be assigned for the, right? So the output will be 101. So the output will be this one. Everybody is clear on this part. You can write yes or no, or you can speak up if you are not clear. Hello. Can you type if you are clear or not? Yes or no?
Sir, the last part, sir.
The last part means this one, or
Priority encoder.
okay,
Uh,
priority encoder. Okay. So let me quickly repeat again everything for you. Okay, everything, and then I will discuss the priority encoder also. Okay. So see, the voltage over here is 6 volt. Voltage over here is 4 volt. This comparator will give output 1 if whatever voltage is on the V plus is greater than 4 volt. Then only it will give output 1, and every other case it will give 0, right? If V positive is less than 0. So that is the simple case. Now what I have done, I have calculated the voltage over each node. So uh, this voltage I can represent like this, right? By 6 into 8 by 8, because this will be 6 only, because 8 will be deducted. I can write like 48 by 8. And see, for every other register divider, it will be one lesser register, right? So the voltage will be dropped like that. So this is 48 by 8. So here it will be 42 by 8. Similarly, here it will be 36 by 8, then 30 by 8, 24 by 8, 18 by 8, 12 by 8, and 6 by 8. Okay, so this value 42 by 8 is greater than 4, so that is the reason why you will get 0. Okay, again, so 36 by 8 is yeah, 36 by 8 is again greater than 0, sorry, greater than 4. You will get 0, right? 30 by 8 is lesser than 4, you will get 1, and you will keep on getting 1 for all the other voltages. Okay, so that's how you are getting output over here. Now what you have to do is you have to find out, okay, which of the output is correct, which of the output is correct. So or what will be the output. So whenever, so encoder is, you give one of the inputs, you will get the output. That's how it is. So you, if you get 1 in the sixth node, the output will be 110. If you get 1 in the fifth node, it will be 101. But what if multiple inputs are 1? Whenever multiple inputs are 1, the priority will be given to the logic with the highest one. Okay, the priority will be given to the logic with the highest one, right? So you can see this is 1, this is 0 0, right? So the priority will be provided to d5. Okay, the priority will be provided to d5. So that, because all the other have the lesser priority, so the most priority is d7, but d7 is not 1. D6 has the second highest priority, again d6 is not 1. D5 is the highest, second, third highest priority, but d5 is 1. You ignore the other ones. Okay, you will get 101. That's how it is that clear?
Yes, sir.
Sir,
Yes, sir.
I didn't understand, sir.
You didn't understand the priority encoder?
Yes, sir. How will we get 101? Because the priority encoder will take the highest priority as 1.
Yes.
Then how it is taking the lowest bit as also as 1?
No, no, no. See, 5 is been converted into binary 101. If it would have been 6, it would have been 110. It would have been 7, it will be 111. Are you getting my point?
Okay, sir. So priority encoder will take the highest bit as 1.
Yes.
But the output will be according to
According to
the
position.
A to D converter.
No, no, it will be encoder. It is not an analog to digital converter, rather than it's an encoder. Yeah. And what does encoder do? Encoder, so if I have an encoder, right, I will have n lines, right? Sorry, 2 to the power n lines, you will get n bit output, right? So if you have 8 lines, you will get 3 bit output. So any of the line is 1. If fifth line is 1, the output will be 101. It's like that.
So is there difference between encoder and A by D converter, sir?
See, in the analog to digital converter, you use an encoder. Okay, that's how you should understand. So so the entire thing is what? Entire thing is A to D converter, right?
Yes, sir.
So this part is encoder. So if I ask what are the components which build analog to digital converter, you will say that, okay, I need a register ladder, okay, I need comparators, and I need encoders. You will say like that. Do you understand?
Okay, sir.
For getting analog to digital output, you have to provide an analog voltage. See, analog voltage is not provided to encoder. Encoder has been already provided to digital voltages, right? And this digital voltage uh, will be used to convert it into an output, which will be the digital output. So, yeah, moving to next question. It is again a simple question, and it is just a question which has been shown previous one. And I just want to ask, okay, if I have a 3-bit flash ADC, what kind of priority encoder is required? It was the previous question itself, right? So if you see the previous question, the answer was 8 is to 3, right? 8 is to 3 priority encoder is required, right? So if you have n bit, okay, so the answer will be the encoder which will be required, the priority encoder which will be required for the flash ADC will be 2 to the power n cross n. Okay, so in this case n is equal to 3. The answer is 2 to the power 3 cross 3. So this will be 8 cross 3. Is that clear, everybody?
Sir, both is class ADC, then it will be 2 power 4 into 4, 16 plus 4.
Yes, if it is 4 bit, it will be 16 plus 4. Yes.
Okay, okay, okay. Thank you, sir.
So moving to, so in this today's session, most of the questions are like that only. Most of the small numerical and theoretical questions. Okay. So this is one of the important question. What is the relation between sampling frequency and the signal frequency to avoid aliasing effect? Anybody knows the answer?
It's A.
Everybody is convinced with this, right? So this is what we call as Nyquist criterion, right? Nyquist criterion, right? The sampling frequency should be at least twice the signal frequency in order to get uh, uh, output without aliasing. Okay, so
So what is the what is meant by highest frequency of the input signal?
sorry, highest
I
frequency of
mean, you have a randomly varying signal, sir.
yes.
So how do you define highest frequency of the input signal? If, it is a randomly varying signal. How do you define it? Is if it is not a periodic signal?
You cannot define frequency for a random signal, right?
Yes, sir. Yes, sir.
See, frequency is only so frequency means what? Frequent. Something is frequently coming, right? Or like this, or like this. Anything which is periodic. If the signal is not periodic, you cannot define the frequency. Okay.
Okay, sir.
For a random sequence, you cannot define the frequency. So moving to fourth part, again a very simple question. Anybody wants to give me the answer? See, this is an 8-bit analog to digital converter, which has a full scale analog voltage of 5 volt. The question is, what is the resolution? Which means, what is the difference between two consecutive values? For an 8-bit analog to digital converter, which has the analog input of 5 volt. Very simple question. I have already discussed this in last tutorial. Anybody wants to answer? Anyone?
19 millivolt.
You're saying A?
19.
You're saying A?
Yes.
Okay.
Yes.
Anybody else? Okay, Vivek is also saying A. May I ask why do you say A?
It
Anybody?
is 5 by 256 minus 1.
Okay, thank you. Okay, so I have one answer which got called as 1.9 millivolt. So let us see. So the output will be 5 volt, right? So the full scale resolution divided by 2 to the power n minus 1. Okay, where n is bit. So this is the resolution. Okay, so if I convert 500 volt into millivolt, so it will be 5000 millivolt. Okay, divided by 2 to the power n minus 1. So 2 to the power n is 2 to the power 8, that is 256. So this will be 255 divided 5000 divided by 255, right? So this will be 19 millivolt if you divide it like this. Okay, so the answer over here is 19 millivolt is the correct answer. Everybody agrees with that?
Yes.
Thank you. Moving to next question. Very simple question. Which of the following technique is used to erase the data in EEPROM memory? Anybody want to answer? Anybody knows the full form of EEPROM?
Electrically erasable PROM.
Yeah, electrically erasable PROM. So the name gives the answer, right? How do you erase the data?
By applying electrical signal.
By applying electrical signal. Okay, so this is answer of this question. So I hope everybody understand this, because the name itself says electrically erasable, so you will apply an electrical signal to get erase the data. Moving to, yeah,
Sir,
any, yes.
sir, can you tell a bit more about how do you electrical erase in EEPROM? EEPROM?
You want me the circuit design you are saying?
No, not circuit like outline what exactly it is meant by electrically erasing the data.
So you apply some signals, electrical signals, and you erase the data. So see, in all the memories we have currently, right? If you want to erase the data, how do you erase, right? So suppose I am giving at a very high. So if you have a memory chip, right, a flash memory, which is in your so which can be considered the SD card. SD card is a flash memory, and you want to erase the data. What you do? You click erase, right, in your mobile phone, and it will erase the data. What is happening inside is whenever you click an erase command, it will generate some electrical signals that is nothing but my bit patterns, right? And it will give the command to the memory that okay, all the data has to be erased. So however the memory has been defined, right, you will write zero in all the memory block. So that's what electrically erasable we call. Do you understand? We have couple of memory designs, DRAM and SRAM. Maybe you will understand when I say what is write data means and read data means. Okay.
Okay.
So moving to the next question, which of the following statements are true? Okay, so let me read out the statements for you guys. The first statement says accessing any memory location of RAM, so random access memory, takes same amount of time. That is one statement. The second statement is accessing any memory location of sequential access memory takes same amount of time. So please note that in this case it is random access memory, here sequential access memory. Low cost memories can be designed using SRAM cell, right? And the fourth is SRAM memories need a periodic refreshing circuit. Okay. Anybody wants to tell me which of the statement is true?
A.
What about other students? Okay, so the answer is actually A. Why? Because it is saying that okay, it is random access memory. Okay, random access memory. It means you randomly access data from anywhere. It should take the same amount of time. Okay, so see, for the sequential access memory, data will not take the same amount of time because you are sequential accessing data, right? The data which are nearer, which will take lesser time, and the data which will be farther will take more time for the sequential access memory. Okay, but for the SRAM or the RAM, the data should come at the same time. Okay, let me put some comments on last 2 points. SRAM memory is one of the costliest memory which we have. Okay, one of the costliest memory in your system, in your laptop or the mobile, where the SRAM sits. Anybody who knows the answer? Where do we have the SRAM memory? Anyone?
Keyboard, sir.
Keyboard? No, not keyboard. Anybody else? So please, what you have to do, you have to go and search this term caches. Okay. So your laptop or mobile will have one kind of memory that is called caches, and all the caches are made up of SRAM. Okay. And please note that SRAM means static random access memory, static RAM. Okay. It means that as long as your power supply is there, as long as your power supply is there, okay, your data will be held. Okay, so it means that the fourth option again becomes incorrect, means SRAM memory doesn't require a periodic refreshing circuit. Okay, so you do not require to refresh the data once written, it will be remaining if the power supply is there. Okay, so SRAMs are found in caches, so you should note this down and you should read about caches, what are caches. Okay, so just giving up more points to you to read. There are three levels of caches which are available: L1, L2, and L3. Okay, in mobile there are L0 caches also. Okay, so you should search it out and you will understand what caches are made up of. Moving to next question, it's again a very simple one. Anybody wants to give me the expression for A and B? This is an AND gate. Okay, and you have to give me the expression for A and B. Anyone?
B.
Okay, I have one answer, that is B. Anybody else? Okay.
Okay, B.
Okay, I have two answers for B. Let us try. Okay, so please note that this AND gate has been connected with two inputs X and Y. Okay, X and Y. So the output will be X, Y. Okay, and this AND gate is connected with again two inputs X and Z bar. Okay, X, Z bar. And this is connected with an OR gate, so XY plus X, Z bar. Okay, so you see, there is actually only one option for this one. Also, we will see the B also. Okay, so this is connected with X and Z. Okay, sorry, X and Y bar. So this will be X Y bar. Okay, this one X Y bar, and this one will be Y and Z, Y Z, and this is connected with three. Okay, X Z bar. So X Z bar plus X Y bar plus X Z. Not sorry, Y Z. Okay, so X Z bar plus X Y bar plus YZ. Okay, so this is the correct answer. B. Everybody understood this? Everyone?
Yes, sir.
Okay, thank you. Moving to next question. Again, a very simple one. If anybody has heard of dynamic random cell, DRAM cell, can anybody tell me how many transistors are in DRAM cell, dynamic RAM cell? How many transistors are in dynamic RAM cell? That's the question. Anybody knows dynamic RAM cell, DRAM cell? Okay, I don't think so. Anybody knows. So, so four. Okay, Sanjay is saying four. Uh, Actually, it is only one. Okay, so let me design a DRAM cell for you. So this is how one DRAM cell looks like. This is the transistor and this is the capacitor. Okay, so you write the data here. This is my Q node, and there are something called as word line WL. This is called bit line WL and B. Okay, so whenever this is one, right? So the data will be red. Okay, and whenever this is off, if this is 0, right, so data will be hold. So at WL equal to 1, right, BL is equal to Q, right, so this is my DD, and holding means at WL equal to 1, uh, Q equal to Q, right, so it will be holding. Okay, and if you want to write again WL equal to 1, and if you have something on BL, it will go to Q. Okay, so Q equal to BL. Now the question here is, how many transistors we have? We have only one transistor. So that is one point. The second point is, as you read the data, okay, if you make WL equal to 1, please make sure that you understand this. This is a capacitor, okay, this is a capacitor, okay, and it will hold some charge over here at this node Q, some charge. Now, as you make this 1, so the charge will flow like this. So data will get lost. Data will be lost. Okay. So that is the reason why periodic reset is required in DRAM. there was one question, right? In that it was written that SRAM require periodic refresh, right? And that was a false option. However, in DRAM, periodic refresh is required. Okay, the data will be lost. So that is one point. And the second point is this transistor doesn't act as an ideal switch. What does it mean? It should be like this, right? Oh, sorry. It should be like this when it is off, right? However, uh, for this transistors there are still some current, very small current which flows from this path, and because of that the 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 capacitor actually discharges. Okay, so in the traditional RAM, for every, so please note these values, okay, these are very important. Every 64 millisecond the DRAM cell has to be refreshed. Every 64 millisecond the DRAM cell has to be refreshed. Okay, after 60 more millisecond, what you will do, you will again the write the data. So this was a little bit high level thing, but I think you should know because we are discussing about DRAM cell. Anybody knows in our laptop where the DRAM cell are used? Anyone in your laptop or mobile where the DRAM cell are used? I want some answer. Okay, so if you don't know where the DRAM cell are used, so whatever we call as RAM, right? Okay, Ranjit doesn't know, doesn't matter. Okay, so whatever we call as RAM, right? So suppose you say that okay, my laptop has 8 gigabytes of RAM. Okay, my mobile has 4 gigabytes of RAM, or 8 or 16 gigabytes of RAM, 16 GB RAM. So that RAM which you are talking about is nothing but DRAM. Okay, so now you have learned something new, and you should go and see, right, that how much RAM you have in your mobile and laptop, and all these RAMs are made up of dynamic RAM or dynamic random access memory. Is that clear, everybody? Now, whatever I have said is that.
So why do you refresh? What is refreshing, and why do you refresh?
Okay, okay. So refreshing means, so see, the job of the memory is to hold the data, right? Store the data. The job of the, so I will delete it. I will just uh, make this cell, right? So the job of the memory is to hold the data over here. Okay, whatever the data, whatever you write, it should store, right? Doesn't matter if I'm seeing after 2 nanosecond, or sorry, 2 second, 4 second, 10 second, right, or 15 second. You don't want your data to get lost, right? In a very higher perspective, if you open Google Chrome in a laptop, you want that it should be opened, right? So whenever you open a Google Chrome on your laptop, the data of the Google Chrome comes into RAM, and you want that okay, it should kept open unless and until you close it, right? So the data should be there. Now what happens because of this small amount of current which flows, uh, because of small amount of current which flows, okay, some leakage happen. Okay, and the charge or the data, suppose one was stored over here. Okay, it can happen that after some time all the charge discharge and it will become zero, and you don't want it, right? You don't want your Google Chrome to close abruptly, right? That's my example. So what you do, you rewrite after every x amount of time. So whatever data is there, you rewrite after every x amount of time, right? And that process is called refreshing. Okay, and that is the reason why it is called as dynamic random access memory, because the data is getting lost every time it is dynamic. Is that clear?
So you said about 64
Millisecond.
micro
Millisecond.
millisecond. Okay.
Yes, 64 millisecond. And please note that this is a very large time. You might say that okay, it is less than a second, but for a VLSI engineer or a semiconductor engineer who are working in nano dimension and nanoseconds, 60 more millisecond is a very high time. Okay, so Okay, moving to next part, and again for Vivek, I will repeat. See, in this question, what we have asked was how many transistors we have in a dynamic random access memory. The answer is one. Okay, so we have only one transistor, and this is how the DRAM look like. There is one transistor and one capacitor. Okay, so if somebody asks, okay, how many components are there? There are two components, one transistor and one capacitor. Okay, uh, yeah, moving to next question. Uh, Now we are talking about SRAM. Earlier we talked about DRAM. Now we are talking about SRAM. And the question is, how many transistors do you have, or how many transistors capacitors you have in an SRAM set? Anybody knows this? Anyone? Okay. By looking in your response, I think you have not watched the videos. Okay. So see, this is how an SRAM cell look like. Okay. This is my transistor. Just see. This is how it looks like. These are my two transistors. Again, these are my two transistors. Okay. Again, you have two more transistors, and this is connected to this node, and this is connected to this node, and here again you have one more transistor. Okay. You call this as WL. Okay. And here it will be ground. You call this as bit BL, and this as BLB, bit line bar and bit line, and this is word line, similar to the dynamic random access memory, right? And whenever you want to write the data over here, so here it will be written Q, and here it will be Q bar. It means if you write 1 here, the 0 will be stored here. Okay. So now when okay, sorry for the glitch. I think the notability is updating. Okay, I was discussing about this, and how do you write into the cell? What you do, you make WL equal to 1, WL equal to 1, right? Suppose if you want to write 1, so what you will do, you will write 1 from here, 0 from here, because you want to store the data. So you will write 1, you make WL1, it means you are turning on this two transistors. Okay, 1 will go here, 0 will go here. Okay, please consider this as this kind of structure. It is nothing but a back to back connected inverter. Okay, so that is the reason why if this node is 1, this is 0, which will make this again 1, right? So infinitely, for infinite time the data will be remaining like this only, right? So as soon as the power supply is there, the data won't get lost. That is the reason why we call this as static time. And the answer for this question is, how many transistors do we have? 6 transistors, right? And these are MOS transistors, MOS transistor. MOS stands for metal oxide semiconductor. Everybody agrees? Everybody is fine with this? We have discussed two cells, one dynamic random cell, another static random access memory cell.
So in the static RAM, RAM is basically it won't the erasable memory, right?
Yeah, it is an erasable memory, yes.
So what is static RAM, sir?
Static means, you see, if you store data 1 here, it will make this 0, and this 0 will make this 1, right? So you once you write, you do not have to worry about the losing of the data. So data won't be lost. Just
Okay, so
like
until deleted, until power
until
off.
it is until powered off, it won't be lost. Excellent. So that's what I wanted to explain. Okay.
Sir, any examples of SRAM cell?
This is an SRAM cell.
No, no, like you given dynamic RAM cell is laptop and mobile in stored. So
Yes.
SRAM, where we have to install it?
I have discussed this. Let me tell you. In the laptop and mobile, uh, there is one memory which is called as caches. Okay. Okay. L1,
Okay,
L2, and L3 caches are made up of SRAM cell. Okay.
okay. Both are in laptop and
Everything. So all see. Uh, you have so many memories in your laptop. Okay. So if I will tell you all the memory hierarchy. Okay. This is good for everyone. So we have a processor CPU which has some registers. Okay. So some registers you have some registers which are very near to processor. These are nothing but flip flops. Okay. This is also memory. After that you have caches. Okay. L1, L2, and L3 caches. L1, L2, and L3 caches. Okay, these are SRAM caches, SRAM. After that, what you have is very big DRAM. Okay, this is what you call as RAM in general in your laptop. After that, what do you have? Again, a very big, right? NAND memory, NAND flash memory, right? So you might not have heard about NAND flash, but you might have heard about SSD. So these are solid state drives. Okay, and and then what you have, the very big hard drive, HDD. Okay, these are magnetic tape memories. Okay, so in your laptop every memory is available. Now if you ask me why so many memories are there, see, your L1, L2, L3 are the fastest memory but have very small size. Why? Because the cost is very high. But the SSD and the magnetic hard drive, right? These are slowest memory, but the cost is very low, right? So if you want to store the data and just keep it, you want to store in SSD or hard drive, okay? But if you want to store some data which is continuously accessed, it means suppose you are playing a game, right? So the game is nothing but a data only. Okay, you should understand this. Every time you play a game, some kind of data movement is going on, and you want that you should quickly access such that there won't be any lag in the game, right? And you want to store those kind of data in your DRAM or in your SRAM. Okay, this is how the memory hierarchy look like, and that is the reason why you have so many memories, because you want to optimize cost also, and you want to have larger uh, memory space also. Is that clear?
Sir, the secondary memory, which is the magnetic memory,
Yes.
um, how will the storage make it permanent, sir?
The storage is permanent only. How does
Uh,
the storage is permanent? You are saying
yes, yes. What is magnetically storing memory?
there are so if you see in the hard drive, okay. Just let me see if I have some pictures of the hard drive. Okay, one minute. Magnetic. If I can draw a picture, okay. So what happens? Everybody knows about the CD drive, right? CD drive, and in that, what you do whenever you want to write into a CD, right? So if this is like a CD drive, right? So you store permanently data like this. Okay, so there is one knob which runs, right? And by using magnetic field, you change the data inside like this. Okay, in the magnetic memory, what happens? You have many disks, one top of the other. Okay, so whenever you want to write into the magnetic memory, you have some pointer which moves and that is the reason why whenever you write in the secondary memory, it makes a noise, right? Because it is rotating, right? And this node will help you to the write data directly into the memory, right? It will be creating magnetic field, and this magnetic field will directly write the data into memory. That's how I think up to that abstraction I can tell.
Yes, sir.
So maybe if you want more detail, I will share you a couple of links at the exact working, and you'll get more points over there. Okay. So moving to the 10th question, again a very simple one. Question is, a combination function can be implemented using LUT, and you have to say in false statement. Okay, a sequential logic can be implemented using LUT. LUT can be used as a RAM memory, and configurable logic blocks contain LUD, flip-flop, and multiplexer. Which of this statement is false? Anybody knows LUT? What is LUT?
No.
This is nothing but as lookup tables, right? If I want to make a LUT of AND gate, okay, AND gate, so it is nothing but uh, the truth table itself. Okay, this is A, B, and this is Q 000110 and 11. Yes, Avinash is saying lookup table, and the AND gate the output will be 01. So I have memory in the 0th row it will be 0, the 0th row it will be 0, and it will be like this. Okay, right? So whenever I want to implement an AND function, what I will do, I will write 0001 such that for 00 I will get 0, for 01 I will get 0, for 10 I will get 0, for 11 I will get 1. But instead of 0001, if I write 1000, it will be a NOR gate, right? So any gates you can implement using LUT, right? So any combinational function, right, can be implemented using lookup table, and you see you can access any of the data at any moment of time, okay, from the lookup table. So it can be used also as a random access memory. Okay, this is one of the things I think you might not know. Configurable logic blocks, CLB, these are often found in one of the hardwares which are called FPGA. Okay, it actually contains LUT, flip-flop, and multiplexes, right? So this is also a true statement. The only false statement here is a sequential logic cannot be implemented using LUT, because LUT is just a lookup table, right? But if you want to have a sequential logic means what, right? Which will work at clock edges, right? If you want to have that kind of logic, you cannot design using LUT. So lookup tables can only be used to design combinational functions. Is that clear, everybody? Okay.
Yes. Could you please repeat why sequential logic cannot be implemented using lookup table?
So suppose I want to implement a counter, right? So counter is what? It keeps on giving 0 0 0 0 0, then 0 0 0 0 1, then 0 0 1 0 0 1 0, then 0 0 1 1, then one something like this, right? 0 0 1 1 0 1 0. So at every clock cycle, it is giving you some output, right? How do you represent this in the form of a lookup table? That's my question. And you cannot do that, right? Because in the lookup table, you provide an input combination, you will get an output combination. It's like a function. Okay, you provide an input combination, you will get an output combination, and all the combinational logics are a function, right? But if the sequential logic, if for every clock edge you are getting some output, uh, that how will you represent using an LUT? That's the problem over here. Okay, so that is the reason why we cannot use LUT to design. It cannot be completely implemented by LUT. That's the point. Okay. 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 So moving to the last question of the day, and this I have already discussed. In a DRAM, I have four questions, four options. Periodic refresh required is not required. Information is stored in capacitor. Information is stored in latch. Both read and write can be performed simultaneously. This is my DRAM cell. Okay. Which of the statement is true?
One.
This is DRAM cell. Please note, this is the DRAM cell. I have discussed that in DRAM, because of the leakage, the refresh will be required, right? Will be required every 64 millisecond. We have to refresh, and here it is written, it is not required. So one is not an option. Okay, so this is wrong. Is the information, where is the information stored? Yeah, it is stored in a capacitor, right? So if this is Q, this is the place where the information is stored. So this is correct. Is it stored in latch? No. Can I do both read and write? That's one of the important points, right? So you cannot do, right? So if you want to read the data, you activate what line, you get whatever Q on the bit line. Okay, but if you want to write the data, you have to activate the word line and you have to transfer bit line to Q. Okay, so both read and write operation cannot be performed simultaneously. You can either read or write at a given amount of time, or get a point of time. So yeah, any question?
Can we rewrite in SRAM? Can we read and write operation can performed in SRAM?
No, the instance in which I have shown, in that also you cannot do both read and write operations simultaneously. No.
Okay, sir.
So see, in the today's lecture, what we have discussed, couple of basics of ADCs, okay, couple of questions on that, and the major focus was on memories. And please note that memories is one of the very important topics in the digital design. It is extremely important. Okay, everybody should understand. Some of the companies which design memories are Micron. Everybody, if you don't know, Micron, Samsung, okay, SK Hynix, SanDisk, okay. So these are the companies which design DRAM, the RAM you talk about, and the flash. Flash means SSD, okay. And there we have Seagate and Western Digital, which design hard drive also and SSD also. Okay, and who design the SRAMs? Every company who design processor are designed using with SRAM. So Intel, TSMC, not TSMC, TSMC is a foundry. Intel, AMD, okay, ARM, Qualcomm, Nvidia, okay. All of these companies design SRAM, okay, in their process, whatever processor you are using. So memory again is a very important topic, right? So whatever we have discussed today is very basic, extreme basic of the memories, okay. But suppose if you in future you want to work with any of one of these companies, memory is the topic. You can go into extreme detail and work in the memory design of any of this company, right? So just a motivation for you guys why you should learn these concepts. So if you have any question,
Thank you, sir.
sorry.
Thank you for your motivation, sir. Thank you.
Okay. So everybody, you should be extremely motivated. Why? Because this is the right time to work in the VLSI domain. You might see the Indian government is pushing extremely hard for the semiconductor thing. And please note that in the next 10 years, it will just create enormous opportunities for the bachelors of electronics, the masters in VLSI, the bachelors in VLSI, if new stream comes up. Okay, so if you are interested in this kind of this field, you should take it up as your career. Okay, and if you want to continue it as your career, and if you want any kind of guidance, you can write to me in this email. I can provide you what kind of subject you should read, what kind of project you should do. I can guide you in everything. Okay, if you want to work in any of these companies in future. Okay, if you have any question, please ask. Okay, if you don't have any question, thank you everyone for joining today's session. We will meet again tomorrow at the same time. So thank you.
Thank you, sir.
Tomorrow.
Thank you, sir.
Okay.